Hello everybody. So welcome back to my channel. As you have seen the various algorithms we were discussing in this channel that are very useful in data structure. While implementing data structure, these algorithms are very helpful. So today we are going to discuss a very important topic of data structure, that is minimum spanning tree. First of all, try to understand these three terms. An algorithm name consists of these three words. So let's just try and understand what these three terms means. Firstly, we are dealing with the word that is minimum. Minimum means that a tree that is going to contain the lowest total weight. So the very first point is, whenever we are talking about minimum spanning tree, we are talking about the weighted graph, because if there is a weighted graph, only then we can say the cost is going to get minimum or maximum, or what would be the cost. Okay, so the very first point that you need to understand is, whenever I'm saying minimum spanning tree, or whenever I'm associating a term minimum with any of the tree or graph structure, so that means what I'm trying to say is that is a weighted graph. Okay, so the second term is spanning. Now what does the spanning mean? Spanning means connects all the vertices of the original graph. So what we are trying to do is, we are trying to create a new structure from the given structure, but the structure that we are going to create out of the given structure, that is going to connect all the vertices, but also keeping in mind that we are going to minimize the total weight. And the third term is tree. Tree means that we have already discussed in our previous lectures, that tree is one of the data structure that is containing no cycle. Okay, that forms a tree structure. If any of the graph is forming no cycles, that means that is a tree structure. So now let's just understand what do you mean by minimum spanning tree. Now minimum spanning tree in algorithm refers to the subset of edges. So first of all, we are talking about subset of edges. Now what do you mean by subset? Subset means that out of the given edges, we are choosing only some of the edges. Now how we are going to make that choice, that depends upon the algorithm that we are going to follow. Okay, within a connected, undirected and edge weighted graph. Now you understand that these three are the requirement, are the prerequisites whenever we are talking about the minimum spanning tree. The very first is, it should be a connected graph. Okay, now whenever I am saying connected graph, so that means every vertex has some connection with the other vertex. Then is undirected, because if your graph is directed, then probably we cannot calculate the minimum cost tree. Okay, so that is the another prerequisite, that your graph must be connected, that your graph must be undirected, and it should be edge weighted. This is the very first point I told you, that whenever we are talking about minimum, so that means we are talking about the edge, the weight on the edges. Only then we would be able to calculate that which one is costing us less, or which one is costing us more. Okay, that connects all the vertices together without any cycle. That is the definition of a tree, that it should not contain any cycle, and with the minimum possible total sum of the edge weights. I hope you have understood what do you mean by minimum spanning tree that we are going to form. Let me just make it simple for you again. So in minimum spanning tree, what we are going to do, we are going to create a new structure from the given tree structure, but that structure is going to give us the less weight. Okay, we are going to make a choice in such a way that the total sum of weights in the whole structure is going to be less as compared to the given structure. And the second point that we need to consider is, our graph should be connected graph. Okay, there should not be an isolated vertex, because if there is going to be an isolated vertex, we cannot work on that. Okay, so the graph should be connected. And the third point is, your graph should be undirected. Okay, because if your graph is directed, then probably we won't be able to make a choice. And this is all about minimum spanning tree. Now how we are going to create that subset from the given set of vertices, that depends upon the algorithm that we are going to choose. Since we have different types of algorithms, we have Prim's algorithm, we have Kruskal algorithms, we have so many algorithms. So the very first in line that we are going to discuss today is, that is Prim's algorithm. Okay, now let's just understand how this Prim's algorithm works. Now firstly, let's just have a look at the definition of the Prim's algorithm. Okay, so Prim's algorithm is a greedy algorithm. As you have seen my previous video in which I have explained what is a greedy algorithm. Actually, we do have different approaches in data structure like divide and conquer, dynamic approach, greedy algorithm. So Prim's is a greedy algorithm that finds the minimum spanning tree for the weighted undirected graph. So these are actually the conditions that should be fulfilled while implementing the Prim's algorithm. The very first condition is your graph should be a weighted graph, and the second one is it should be an undirected graph. Now it finds the subset of the edges that forms a tree that include every vertex. Now we are going to work on the edges. We are going to choose the edges in such a way that it is going to minimize the cost. Okay, we are going to form a subset of edges out of the given edges, but that choice should be made in such a way that no vertex should getting compromised. Okay, where the total weight of the edges in the tree is minimized. See, we have only 2 points that need to take care of while implementing the Prim's algorithm. The very first point is that we are going to look only after the edges, that we are going to make a choice of those edges which is going to minimize the cost. That is the first point. The second point that we need to consider is that we cannot compromise any of the vertex. If I am saying we cannot compromise, which means that every vertex should be there while making a new graph. Okay, there is one more definition, that Prim's algorithm is a minimum spanning tree algorithm that takes a graph as an input. Yes, definitely it is going to take a graph as an input, and it is going to find out the subset of edges of that graph which forms a tree that include every vertex, has the minimum sum of weights among all the trees that can be formed from the graph. Okay, so we are going to make a graph from the given graph in such a way that cost should be getting minimized, but every vertex should be there. So this is the definition of the Prim's algorithm. You will be going to understand it in a very clear manner with the help of example. So let's just have a look at the example also. So let's just have a look at minimum spanning tree using Prim's algorithm. So first of all, we need a graph. So this is my graph. So there are some prerequisites of the minimum spanning tree. Right now we are not discussing whether it is a Prim's algorithm or which algorithm. We are just saying that in minimum spanning tree we have discussed the 3 points. The very first point was your graph should be connected. So as you can see, yes, my graph is a connected graph. Second point was it should be an undirected graph. So as you can see, there are no direction between the edges. Okay, there are no direction labeled on the edges. And third point was it should be a weighted graph. So these are the desired weights on my graph. Okay, now we are going to form a minimum spanning tree out of the given graph. Okay, so first of all, we need to choose a starting vertex. You can choose any vertex as the starting vertex or root vertex, since it is not given. Okay, if we are not provided with the information that this is your root vertex, we can choose any vertex as the root vertex. So right now I am choosing A as my root vertex. Now we are just going to focus on the edges, on the weights of the edges. Okay, A is having 3 edges that are connecting it to E, B, C and D vertex. Now we are not really concerned with the fact that with which vertex A is getting connected to. We are only concerned with the fact that we are going to make a choice between the edges, and we are going to choose the edge that is costing us the minimum. Okay, so now let's just look at the weights or the cost on the edges. So if I'll consider this edge that is costing is from A to B, that edge is costing me 6, from A to C edge is costing me 1, and from A to D edge is costing me 5. So it is very clear from the given edges that out of 6, 1 and 5, 1 is costing us the least. So we are going to make a choice of this edge. Okay, so the next thing is we need to look at all the edges that are either connected to A or C. As we have already seen the edges that are getting connected to A to C choice has been made already. Now we need to look at A to B, A to D, that is costing me 6, 5, and all the edges that are connected to C. As you can see that out of all these edges, this edge is costing us the least, that is from C to F. So the edge which is costing us the least, definitely we are going to make a choice of that edge. That means in our graph, the graph that we are creating, we have make a choice that is from C to F. Now look at all the edges that are either connected to A, C or F. Okay, you need to look at all the edges. So if I look at all the edges out of A, C and F, so we are going to we can see, as we can see from F to E, there is a edge that is costing us 6. This edge is costing us 4 that we have already chosen, and this edge is costing us 2. So definitely we are going to make a choice of that edge which is costing us the minimum, that is 2. So we are going to make a choice of 2, that is from F to D. Now if you look at D, see, now you need to consider again you need to recall the definition that a tree is the graph which is containing no loops. So if I look at this edge from D to A, that makes a loop, because D to A we have already a connection. That is, whether it is direct or indirect, that is not the point. Okay, we already have a connection, so we are not going to make it a loop. Okay, C to D we already have a connection, so we are not going to look at this. Now you need to look at the fact that which vertices are left. Okay, which vertices are left. If I look at D vertex, it is having a connection with A, that is already been visited, with C, that is already been visited, with F, that is already we have chosen. Okay, so we don't look at the edges that are being connected to D, because that doesn't make any sense. Okay, that is either forming a loop or you can say that will make us reach to those vertices that are already been there in our list. Okay, so let's just leave that. Now look at the fact that we are left with these two vertices which are not visited right yet. So we need to make a visit to these two vertices, that is B or E. So if you look at this C vertex, that a choice that we have already made, that C is having a connection with B and C is having a connection with E as well. Okay, C is having connection with both the vertices, but out of C to B, if you look at the edge C to B, that is costing me 5. From C to E, there is an edge that is costing me 6. So definitely, since we are greedy, since we are following a greedy algorithm, so we are going to make a choice between C to B, that is costing me 5. Okay, so I have make a choice. Fine. Now there are two options. Either you can connect from C to E, that is costing us 6, or you can connect from B to E, that is costing us 3. Again we are greedy, so we are going to make a choice from B to E. Okay, so this is my choice. So see, first of all look at the vertices, because vertex should not be compromised. So I have covered all the vertices. Okay, your graph should be connected. Yes, my graph is connected, since we are not saying that it should be fully connected. Okay, so that is the case. My graph is connected, that is it. And the last condition was we are going to make a choice in such a way that cost should get minimized. So now let's just calculate the cost. The graph that we have created, that is costing us 15, but the graph that was already given, that was costing us 35. So that means yes, we have minimized the cost by keeping in all the constraints that are in the definition of Prim's algorithm plus in the definition of minimum spanning tree. We have make a subset of edges out of the given set of edges, and we have made a choice in such a way that cost is getting minimized. Okay, so this was Prim's algorithm. So as we have discussed the example, now it is going to be easier for you to understand the actual algorithm step by step. Okay, now let's just have a look at the Prim's algorithm. After looking at the example, I think it is going to be very easy for you to understand the Prim's algorithm step by step. So for the very first step says select a starting vertex. That we have already discussed in example, that you can choose any vertex as a starting vertex or the root vertex if it is not given. Okay, second, repeat step 3 and 4 until the vertices adjacent to the visited vertices but not yet visited. If you can just recall the example, that after visiting A, C, D and F, what we were saying, that we need to visit B and E. So we need to, after making a choice of the edges, we need to select those vertices which are not visited yet, but they are adjacent to the selected vertices list. Okay, the third point is select an edge containing the tree vertex and the fringe vertex having the minimum weight. So we need to select an edge in such a way that the weight should get minimized. We have also used one term, that is a fringe vertex. Now what is a fringe vertex? The vertices that are adjacent to the visited vertices but not yet visited, they are known as fringe vertices. Okay, I'll show you that once again. What are fringe vertices? What is the definition of fringe vertex? Fringe vertex are those vertices which are adjacent to the vertices that has already been visited but they are not visited yet. If you can just have a look at the previous example, if you can just have a look at this example, when we were saying this graph, when we have made a choice till this point, we have covered A, C, F and D. Now B was adjacent to C. C is already been visited but we have not visited B yet. So B is a fringe vertex in that point. Similarly, we have not make a choice we have not visited to E, but the vertex that is adjacent to C has been already visited, so E becomes a fringe vertex in that. Okay, fringe vertex is a vertex that is adjacent to those vertices that has already been visited, but that vertex has not been visited yet. So that means if I am saying A to C, suppose if I am starting it from A to C I have already chosen. Now A, C, adjacent vertices, which are the adjacent vertices of C? That is B and D. I have already visited C but B and D are not visited, so the B and D right now they are fringe. So the next point was add the selected edge and vertex to the minimum spanning tree. This is what we were doing. Firstly we were making a choice and then we were adding it to our minimum spanning tree. We are creating a new graph. Okay, so then exit. You need to keep on repeating step 3 and 4 until and unless all the vertices are getting covered. Once you covered all the vertices, you need to stop. Okay, so this was the definition of your Prim's algorithm. Now let's just have a quick look at the complexity analysis of the Prim's algorithm. Complexity analysis of the Prim's algorithms is order of V square. V is your set of vertices, or N square, E is the number of edges in the graph. So why we are saying the complexity is V square? Because in case of Prim's algorithm, what we are supposed to do, we need to visit every vertex at least once. So if there are 10 vertices, so that means we are going to make that calculation 10 times. Okay, and why we are going to give it a mod? Why we are modding it? Because there could be a possibility that weights can be negative also, because in the definition we have just mentioned that our graph should be directed graph, but we have not said that it should be a positive edged graph. So there could be a negative weights on the graph also, and if there are negative weights, we are just saying that it should get converted into the positive value. Or it could be order of N square. Why? Because we are calculating every edge one by one. Okay, and there is one more point that you need to keep in the mind, that complexity of Prim's algorithm also varies. That depends upon the data structure that you are using. What kind of data structure you are using, whether you are using arrays, you are using linked list, so that varies according to the data structure. One point that you need to consider, I have highlighted that in red. Prim's algorithms are mainly used in the dense graphs. Now what are dense graphs? That we'll discuss in our upcoming videos. So this is all about your Prim's algorithm. Hope you liked the video and you understood the concept of Prim's algorithm. Let's just meet in the next video. Till then, take care. Bye bye.